Good morning, dear students. Today we will be discussing and learning something on the theme, can matter change its state? After this discussion, you will develop understanding of concepts like how states of matter changes, melting point, boiling point, latent heat of fusion, latent heat of vaporization. You will develop the ability to acquire and use the methods and processes of science such as observing, questioning, planning investigations, collecting information, analysis and interpreting data, communicating explanations with evidences, justifying explanations, and thinking critically. You will be able to conduct experiments. You will appreciate how concepts of science evolve with time. You will develop scientific temper in terms of objectivity, critical thinking, etc. You will be able to nurture your natural curiosity. What are the learning outcomes? Classifies materials based on properties or characteristics, such as classification of matter based on their states, solid, liquid or gas. Plan and conduct investigations or experiments to arrive at and verify the facts, principles, phenomena, or to seek answers to queries on their own, such as what is the effect of heat on the state of substances, what is the effect of compression on different states of matter, explains processes and phenomena such as principle of melting, boiling, freezing, measures physical quantities using appropriate apparatus, instruments and devices such as temperature using thermometer, draws conclusion such as matter is made up of particles. Can matter change its state, right? And to understand this particular theme, I have taken into consideration a very common substance without which nobody on us can survive in this world, and that is water, right? And as you all know, water is there in nature in three states. And what are those? Solids, liquids, and gas. Water in the solid state, we call it as ice. And in the liquid state, it is water and this is water vapor. Having said that, there must have been some queries inside your mind, right? Like, how do we connect this? How do we understand all these things, right? So we would like to understand, we'll try to understand what happens inside the matter when there is a changeover from solid state to liquid state and from liquid state to gaseous state. That is one aspect. And secondly, we'll also try to understand what happens to the particles and overall how all these changes take place. Dear students, you all have experienced science, learned science through different experiments. Science is very joyful and enjoyable when we do some activities, isn't it? So let us try to learn something by doing some very small activities. Let us begin this activity. It's an empty beaker and I have some ice on my hand. I have put this thing. And now we would like to see the change of temperature on the states of matter. Well, I'll put this thermometer here, and then we will notice the temperature here. And what we will see is that the temperature is not rising. Okay? And then we will put this thing on the burner, and then we will light up the spirit lamp and slowly increase the heat. Okay? And what you will notice that as this solid state begins to change into liquid state slowly, the temperature is not rising. Okay? And as you increase the heat, as you increase the temperature, at one point of time, this whole ice will get melted into water. And even then, when this whole ice gets completely melted into water, the temperature is not rising. Okay? That's a very interesting phenomenon. So why is it that the temperature has not increased much, even though we have ignited, we have heated the ice, and the ice has changed to water? Now this is something which I will come into. Now see one thing, let me tell you that when the complete ice changes over to water, that means from the solid state to the liquid state, there is a temperature involved. Okay? And that temperature we call it as melting point. Okay? So melting point is basically the temperature under atmospheric pressure at which the solid ice changes into liquid water. Okay? And then again, from that particular point, okay, if we go on increasing the temperature, at one point of time, the liquid water changes into water vapor. Okay? Now you must have noticed that I have uttered the term time. Right? See, time is a very important factor. Okay? Even though we know that the change of state of matter takes place at a particular temperature, for that to happen, there needs to be some amount of time span involved. Okay? You do not get ice instantaneously if you put a cup of water inside a deep freezer, even for say 1 minute. So there is no instantaneous change of state. So please remember, time is also a very important factor. Okay? Right. Now here I would like to tell you one thing, right? While doing this activity, you have to note down certain things, right? When I put the ice inside the beaker, right, at that point of time, you please note down the temperature reading. Okay? And then when the complete ice melted into water at a very light heat over a period of time, you again note that particular temperature. Then you will understand what I have said, that there is no significant rise in temperature at all. Right? Now where has that temperature gone? That is something which we will again try to understand. Right? Now you see one thing, again when you increase the temperature, the liquid, okay, it starts bubbling. You see a lot of vibrations, lot of energy conditions have come up, high energetic the liquid has become, right? And then slowly vapors come up, right? You must have noticed that every day in your home when your mother prepares a cup of tea, right? Okay. You see one thing here, where does the temperature go? Because you have been, you have put the heat, the temperature has increased for you, right? Because you have increased the heat, okay? And the ice has slowly melted into water, but you don't see significant rise of temperature, right? So where has that heat gone? Okay. Now you see one thing, that heat was basically absorbed by that matter. That heat was used to break the shackles of that solid structure, right? You know one thing, that every solid has got some definite internal atomic arrangement. There is a bonding of attraction between the different particles of the solid. Now when you ignite a lamp and when you increase the heat energy, that heat energy is basically utilized to break the attraction between particles of the ice, okay? And then the ice starts to melt, okay? So that is a changeover which we see as the temperature is increased, the kinetic energy increases. And when the kinetic energy increases, there is a lot of random motions that we see in the particles. So here we come to again another point, as I said, melting point. Something which I have explained to you earlier. Let me again tell you that melting point is that particular temperature at atmospheric pressure at which there is a change of state from solid to liquid. So in case of this particular example, right, the melting point of water we all know is 0 degree centigrade or 273.16 Kelvin. So this is the temperature at which the melting of ice takes place and water starts to form. As I told you that when we were increasing the temperature, increasing the heat, okay, and the ice was beginning or in the process of getting melted to water, we did not see any significant rise in temperature. Now why that happened, right? So at this point, I'll bring to you a scientific term which we call as latent heat of fusion, right? And in order to understand this particular theme, let us look at this particular graph. So in this particular graph relationship, what we see is that, okay, you see along this x-axis we find there is increasing internal energy. That means heating is going on, okay, it is reflected, and along this y-axis we see the temperature is increasing. Now what we see here is that as the heating goes on, the temperature increases, right? The solid at one point of time melts, okay, and during this period, during this phase where the melting is taking place, do you see any significant rise in temperature? No, the temperature is not rising. So it is more or less constant, right? But then the heating is going on, right? So where has this heat come? Okay, this heat was used by the system to break the shackles of attraction between the particles of matter, right? Which I explained to you earlier on, right? So this heat was used to break the bonding between the particles, and thereby a change of state took place from solid to liquid. Okay, so if we have to define the term here, we define it by latent heat of fusion. Now what is this latent heat of fusion all about? It says that the amount of heat energy that is required to change 1 kg of solid into liquid at atmospheric pressure at its melting point is known as latent heat of fusion. So for particles of water at 0 degree centigrade, it has more energy than the ice particles at that same point of temperature, right? Let us look at this particular figure in order to understand what happens when we go on increasing the heat. See here, this A, do you see the particles? They are tightly packed. And as I told you, in solid, the internal atomic arrangement is very much structured. Now, in case of liquids, you see the particles, but there are gaps in between. Okay, that means the bonding is a bit weaker than what it is in the solids. But in case of gas, you see, it is very, very loose. Let us try to understand what happens in this changeover. Okay, because you have already understood the changeover from solid to liquid. Now, when we supply heat energy to water, the particles start moving even faster. At a certain temperature, a point is reached when the particles have enough energy to break free from the forces of attraction of each other. At this temperature, the liquid starts changing into gas. The temperature at which liquid starts boiling at atmospheric pressure is known as its boiling point. Now please remember, boiling is a bulk phenomenon. I will again refer to the example of making tea, right? You must have seen water being poured into the kettle, right? And then put over on the gas stove, gas burner, and after some time, vapor starts coming out. But even though you see the vapors, don't you see the water still there? Has all the water changed into vapor? It can happen. That can also happen if the heating goes extended for a longer time. Again, the factor of time, right? Now, particles from the bulk of the liquid gain enough energy to change into vapor state. As I said, not all particles will change instantaneously into vapor state. Bulk of the particles will have enough energy to change into vapor state. And in case of water, this particular temperature is 100 degrees centigrade. So we learned that the changeover from ice to water, it took place at 0 degrees centigrade, and here in case of changeover from water to gaseous state, it is at 100 degrees centigrade. Okay, now you can convert it into Kelvin. So Kelvin is 273.16 Kelvin, and here it is 373.15 Kelvin. So these are the temperatures at which the change of state takes place, right? Now here I would like to come into another term, to discuss another term. Earlier we discussed about latent heat of fusion, right? So latent heat of fusion, it was concerned about that particular phase or that particular temperature where the changeover from solid state to liquid state takes place. But then latent heat of vaporization is that state where the changeover from liquid to gaseous states takes place, right? What is this latent heat of vaporization then? As I told you, it is similar to the latent heat of fusion. It is the amount of heat energy that is required to change 1 kg of liquid at atmospheric pressure at its boiling point, and it is known as the latent heat of vaporization. Here, the particles in steam at 100 degrees centigrade have more energy than water at the same temperature. And this is because the particles in steam have absorbed the extra energy supplied in the form of latent heat of vaporization.